All right, so here we have a roller coaster, which lifts the car 700 kilograms to point A at height 90 meters above. The car is brought to rest at point A, and then it rolls down the incline and follows the track where it flies off, where B is at 50 meters. All right. Work done by the roller coaster to lift the car to maximum height of 90. So we got a couple of options when it comes to work again. It's changing K, force delta X, or basic definition of work, which is the change in energy. Now, K is going to be hard. We don't know any velocities, so we can't really calculate kinetic energy. So let's try work change in energy first. Well, change in energy from where to where? From the ground to the top. So here to up here. Well, how much energy did it have when it was on the ground? Didn't have any energy, or no potential energy. Assuming it was at rest, it doesn't have any energy total. So when it goes up to point A, what type of energy did it obtain? It gains potential energy. So remember, that change, that delta, is final energy minus initial energy. Final energy, like we said, is potential. MGH, you can plug in MGH at this point. And the initial energy, like you mentioned, is 0 because we're on the ground. So really all we're doing is saying that the work is equal to that potential energy at the top. So the mass, 700 kilograms times gravity, which we'll estimate with 10, times the height of the roller coaster, 90 meters. 90 times 10, 900 times 7, 63, with 4 zeros. Uh, 630,000 joules. That seems like a lot, but it's a very, very heavy object at a very, very high height, so it is acceptable. Maybe. What's an elephant weigh? A ton? So 2,000 pounds. It's all good. You can't always do physics. Yeah, I mean, yeah, basically you are lifting an elephant up 90 meters. Well, what do you think? A roller coaster filled with people, right? Same weight as an element? Calculate the energy when it's at rest at point A. It's the same. Yeah, we just did that. Basically, we just calculated the potential energy at the top, which is the answer. So there's your gimme. You could say that an arrow would be sufficient here with the answer 6,300. That shows me that you know that you just calculated the potential energy. Very specific at rest at point A. All right, on the figure above, draw the point P which maximum speed is obtained. Where is maximum speed obtained? Bottom of the hill. This is the point P where all of the potential energy which was up here stored is now in the form of kinetic down here at the bottom. So it's turned from that height energy into velocity energy. The value of the maximum speed at point P? Correct. Yeah, you're doing a conversion between potential and kinetic. So the conservation of energy equation would be potential at the top, goes kinetic at the bottom. Well, you've been solving for potential at the top all the way through here so far. 6,300 joules equals 1/2 mass times velocity squared. UG is a gravitational potential energy. And don't forget to take square roots on these. Common thing to do. 42 meters, or you can just take your CAS out and type in the equation and say solve. Cheaters. 42 meters per second. Yeah, what was our roller coaster yesterday going on? What did we say that was? I don't know. 42 meters per second is 94 miles an hour.
That's too fast.
94 miles an hour. Speed of the car at point B. Now here's where you have your options. So you identify it as a conservation of energy. You can start it here, you can start it here, but you've got to finish it at point B. Point B's got to be one of those points. Started at A. It really, well, A is a little bit easier. Or what's the energy at A? Now the trick is to remember at B, not only do you have a height of 50, meaning that you've got potential, but assumably you're still moving, so you have that kinetic as well. So there's two different types of energy at that point. A lot of people forget the fact that it's got potential energy as well. It's off the ground. It means it's got potential energy. Yeah, see, it's at a lower point than here. This roller coaster can go up and down, and as long as it's frictionless, as long as it's below point A, it will continue going up and down, up and down. Doesn't matter how steep the hill is, doesn't matter how shallow it is. As long as it doesn't go above point A, it will always have enough energy to continue moving. If it got up to point A, then the velocity would go down to 0 at that height. So all of the energy is used to get back up to that point, so it doesn't have any energy left to continue moving. So if the roller coaster for some reason decided that, the designers decided that they were going to do one of these things, well, you get up to here, and then you'd start going backwards. Once you got up to A, all this 6,300, 630,000 joules is now needed to get you to that height. So it's then stored in potential.
So are we making point B that didn't work?
What? Now, that's not even factoring in friction. It's a perfectly frictionless surface. If it had any friction at all, then the hill couldn't go even close to that.
Okay, so
starting gravitational potential. And we started at the top of that, so we still know that we started with that much. Are we making that 0 now? You can, if you want, but that changes your initial number. Because so far in the problem, we've assumed that this is height equals 0. So that 90 was included in this value.
So which are you going from now? Are you going from B?
We're going to start at point A and go to point B.
Why does that not have B plus? Why doesn't it have a K? Yeah.
Because when we get it to the top, we're going to bring it to rest before we let it go down. Mm-hmm. Yeah, that's kind of what we're doing. So we looked at the potential here, which was 6,300. We'd solved that before. That potential turns into both kinetic and potential here. The kinetic energy is 1/2 mass times velocity squared. We want to know the velocity. And the potential there is 700 mass times 10 gravity times the height is 50 meters. So solve for velocity. That ends up being whatever that number is. Actually, it might have been just simpler to do it from point P to point B.
Because you know that it's, I guess if you do point A, you have
I mean, technically, they're of exact equivalent difficulty because the equation ends up being exactly the same. Because even if you take just the kinetic energy is 6,300 because that's where all the energy is stored up. So the equation from B, from P to B, the equation from A to B ends up being the exact same equation, just because the initial energy that you have at both points is the same. If you really wanted to make it hard, choose that point. Oh, that's a good question. What if you chose a point which was exactly on the hill at the same height as B? Convenient, you'd say the height there is 0. So it's just an extension. I don't even know if this works. You'd have kinetic energy at point wherever that is equals the kinetic energy at B. So 1/2 mass times velocity at this point squared equals 1/2 mass times velocity at B squared. You can't. All you prove is that the velocity at that question mark is equal to the velocity at B, which is true, but it won't help you solve it. So choosing that point doesn't do anything except prove that your velocities at that height are going to be the same, which I guess is useful. Right here, if you calculated your velocity at any point where you cross back over that height, you would have that same velocity. Not as you're going down the hill, right?
Oh, that's at the height. That's at the top.
Right. If you were up here, then this would be velocity 0 again. That's interesting. I've never seen that before.